Now we're going to talk about what is, I would say is my favorite engineering tool. It's a very, very powerful tool for dealing with partial differential equations or ordinary differential equations. And it is incredibly useful from an engineering perspective. It's a hard tool to use well. I'm going to introduce you to it, and hopefully some of you will really understand it and be able to use it because it is very powerful. But it is, something that people, can make mistakes with and do stuff wrong, even people that are pretty good. So it's called scale analysis. And what scale analysis does is it says, look, a lot of these terms, these complicated differential equations, we can't really solve them, but we can learn a lot about them, not by solving them, but by kind of reading them and understanding what they're really saying and putting in some sense of how big things are. And we can actually get some really, really useful engineering information from them, even if we can't truly solve the problems. So this is a tool I really like a lot, and we're going to try to introduce you to it and use it a bit on some of these problems. So the basic idea is if you have a term like du dx, so, you have to solve that to find du dx. Requires a very precise solve. But you don't need a precise solve to know basically what it's saying. What it's saying is how much does u change over some length in x in the problem? And that's what derivatives are always asking, is how much does the top thing change as you change the bottom thing? So we don't exactly know what that is at every point in the flow, but you can often sort of get a sense for how big it is. And so you don't use an equals sign when you're doing scale analysis. You use this squiggly sign. And this squiggly sign here means of order. So it means we're not even asking, we're not saying is this like 2.3 or 7.2. We're saying, is it about 1 or is it about 10 or is it about 100? We're looking for an order of magnitude here. And you could think of it also as just being kind of the size of. This thing is about the size of this. It's not equal to it, but it's going to be about that size. And from an engineering perspective, that often is really what you want to know. Is this thing, how heavy is it? Well, is it as heavy as an elephant or is it as heavy as a mouse? That's really going to change your, what you need to do from an engineering perspective. And that's the first thing you really want to know is sort of like, is this thing truly heavy by the scale of what I'm working with, or is it really not very heavy? And so that's the kind of thing we can learn from scale analysis. So if you look at the solid plate here, so this is just a classic flow over a plate. So imagine a plate sitting here. There's an airflow going over it, or a water flow, doesn't make any difference at this point. So we say that the velocity of the flow over the plate is u infinity. And so you'd say in this problem, can we get a sense for how big the u dx is? Well, how much does u change? Well, u changes from u infinity, which is the fastest velocity that I see in this flow regime, to 0. It goes to 0 because there's a no slip condition on the plate, right? So because there's no slip condition, there is 0 velocity in the flow. One of the errors that happens a lot that people aren't good at scale analysis do is they always assume that the flow is going to 0 somewhere when it's not. This is asking you how much does u change in the flow. If u only goes from u infinity to, say, u infinity over 2, well, then that's not right to say that it's going to go all the way to 0. It doesn't. But in this case, it does. There's a region in this flow where u equals 0 because on this plate, u does equal 0 because of the no slip condition. So that top piece is u infinity minus 0. That's how much u changes in this problem. And what's the length scale in x? Well, there's only one length scale in x in this problem. It's the length of the plate. So L is the length scale. Again, we're looking in the x direction because that's du dx. So this is saying that, we don't exactly know what du dx is for this problem, but we think it's about this big. So that's what the kind of thing that we can get from scale analysis. All right, now let's add a little step to our flow. So we'll say, all right, that was du dx for that. Now let's take a plate that has a bump in it. So it's going to be bump like this. Has a little h here. That's the little step size here. And we're still going to have a length of L for the entire plate. So we have L. The flow is coming along the top here at u infinity again. And it's going to flow over this plate, and then it's going to hit this little bump, and it's going to bump over that. So that's our new problem. And now we say, all right, well, du dx hasn't changed. So du dx is still going from u infinity, this fast part of the flow, and it's still 0 at the no slip, no slip solid surface. So we have u infinity, and we still have the x length is still this L. But what is dv dy? All right, so let's try to find dv dy. So I'll hit the, we can see, I'm going to hit the focus here, see if we can get a little better. So what is dv dy? So v is the v velocity. Now, how much does v change in this problem? I don't know, let's try to figure it out. dy isn't too hard. The only y scale in the problem is our little bump h there. So I'm going to say that dy is of order h. That seems pretty clear. My problem is v. V definitely goes to 0. First of all, it's 0 right out here where the flow is just parallel to the x direction. I'll say this is x and this is y. So it's parallel to just the x direction, so there's no v velocity here. And in addition, there's a wall, so it's going to have no slip. So we definitely know that v goes to 0, but the question is, is v ever not 0? And so I'll say v equals 0 at wall and in free stream, far from the wall. V is 0 in both those places, but how can I find how big v is when it's not there? Because it's going to clearly be non-zero here. It's going to have to go up and over this wall. So there's going to be a v right here as it goes across this bump. But how big does that get? Well, let's see if we can figure it out. We have the x momentum equation won't help us with that because it doesn't even have, has v in it only in one place. It's not going to be helpful. So we're going to try to use the continuity equation for this. So in 2 dimensions for incompressible flow, the continuity equation is pretty simple. It's du dx plus dv dy is equal to 0. So that's our mass conservation. And I know du dx. Du dx, I said, well, I think it's the size of u infinity over L. And I also know, I'm going to put a comma here, I'm looking at some v that I don't know, and then I have 0, because I know v goes to 0, and that's divided by h. So that's my dv dy. It's whatever v is, the thing I'm trying to figure out, minus 0, because v does go to 0, divided by the length scale in h. And because these are the only 2 things in this equation, they have to be the same size. They have to. You can't make something go to 0 by adding 2 things of different sizes. If you have an elephant and a mouse, and you add them and subtract the mouse from the elephant, you don't get 0. You get an elephant minus a little chunk of a toenail. So you have to have things of the same size if they're going to add up to be 0. So this u over L has to be the same size as v over h, which means we can get a scale for v. We don't know v, but we can say that the scale for v in this problem is h over L u infinity. That's our scale. So here's a good engineering, result. We're like, yeah, do we know what v is here? Not exactly. Do we know the fastest velocity upward in this problem? No, not exactly. But it's gonna be, we think, about this big. It's gonna be related to how h and L are related to each other times u infinity. As drawn, it's clearly going to be much smaller than u infinity. It's just a little bit of upward velocity here to get over the hump. But this gives us a sense for how big it can be.